Welcome to our demonstration of jFULPAL, which stands for Java-based fuzzy linear programming based on aspiration levels. By means of jFULPAL, linear optimization problems with multiple objectives and fuzzy parameters can be solved. What is a fuzzy parameter? A fuzzy parameter can be a parameter which can't be described by just a single value. It is represented by a set of values, which is shown in the figure. In our case, an appropriate budget for a certain department is illustrated. A so-called membership function assigns each value a membership value between 0 and 1. 1 means that the fuzzy parameter is represented very well by means of a certain value. Values with a membership value of 0 or very close to 0 represent the fuzzy parameter not or poorly. In our example, a budget of 180,000 is necessary, but 180,000 is quite low. 200,000 would be appropriate, but also 210,000 represent the set of an appropriate budget for a certain department very well. Any amount greater than 210,000 is not perfect, representing the set of an appropriate budget very well, and 230,000 is the absolute limit. It describes an appropriate budget for this department poorly. Like the next figure shows, constraint borders can be modeled easily. In our example, we just have to respect an upper limit. All values lower than BI get a membership value of 1 assigned. The point with a membership value of 0.5 represents an aspiration level of a decision maker. According to his opinion, anything beyond the aspiration level is not acceptable. However, also values lower than BI plus DI would be at least theoretically possible. So how does the approach work now? At first, the decision maker has to enter all the input parameters, which can be crisp but also fuzzy. Then it's possible to specify the aspiration levels for each constraint or each objective. More data is not necessary. jFULPAL approximates piecewise linear membership functions based on the input. If no aspiration levels are entered, defaults are set automatically. The software determines the unknowns by maximizing the optimal degree of satisfaction, which is called lambda star. Lambda star is representing the maximized minimal degree of satisfaction concerning all constraints and the goals. These are the evaluated results for the constraints and the achieved objectives by means of the related membership functions. In case lambda star is greater than 0.5, a solution is found that fulfills all aspiration levels of the decision maker. Therefore, he can accept this satisfying solution, or he can improve some aspiration levels in case lambda star surpasses all aspiration levels. If lambda star is lower than 0.5, no acceptable solution can be found, and the decision maker can modify aspiration levels. The solution space can be explored iteratively until an acceptable solution is found or the decision maker terminates the process. So much theory in advance. Let's go for the demonstration. In the initial view, you see different models, which were already entered. Each of them having different iterations, or you could also say different versions. If an iteration is opened, an editing screen is displayed where the model can be adjusted. Objective and constraints are displayed in a list. Each element has a coefficient and a right-hand side as well as an aspiration level. You can set aspiration levels either manually or do an initial computation to get default values for all the aspiration levels. If we click on the Compute button, A solution which maximizes the minimal degree of satisfaction concerning all constraints or the goals is generated. In our demonstration case, we get a solution with a lambda star value of 0.667, which surpasses all the aspiration levels. Let's have a look at the computed solution. It can be displayed in the next tab. However, since the computed overall lambda star is larger than 0.5, we want to make some adjustments to our aspiration levels. Since models can be very large, it is useful to display only the critical parts where fuzzy parameters are involved. In our case, we use the fuzzy filter to display all the constraints where we have fuzzy borders. As you can see in the view, an aspiration level can be changed easily. For example, we changed the aspiration level of constraint number 15 to 7000. There are also other options to change the aspiration levels. One is available in the Aspiration Level tab. As we can see, it is also possible to adjust the aspiration levels by sliders, by entering the value in an input field, or by setting the aspiration level back to a default value. Additionally, another view can be used to adjust the aspiration levels. In this view, the membership functions of the fuzzy values are displayed. We have scrolled already to C15 and the left-hand side is crisp and displayed as blue straight line. The right-hand side is fuzzy and is displayed in red. The lambda value is depicted as green line. Also, the aspiration level can be seen, which is visualized by means of the black line. If we switch on Always Compute, we can activate a real-time computing mode if parameters are changed. Now we adjust the aspiration level concerning the resource consumption of constraint number 15 to a lower value, in our example 6200. The lambda value has not decreased significantly, so we become more demanding and we change the aspiration level of the objective function. The aspiration level is set to 201,900. Now we see that the lambda value dropped down to a value which is less than 0.5. So because the objective is important to us, we decide to relax the aspiration level for a constraint. We go to constraint number 21 and relax the aspiration level to 34,200. So a new lambda value of nearly 0.5 is achieved. If we have a look at the computed solution, we can see that x3 is near 6,200 and x9 is near 34,200. As you could see, uncertainties can be modeled directly. It allows decision makers to use fuzzy parameters. To find an acceptable solution, the solution space can be explored iteratively. So we hope that you have enjoyed our little demo. Feel free to contact us if you like to have more information about FULPAL. Thank you very much for your attention. To get more information, you can have a look at the references which are listed here. Finally, a few acknowledgements. Many thanks to Michael for his great support all over the years and for making the Java version possible. And many thanks to Heiner for his excellent ideas and his scientific advice.